Welcome to the VG Lab podcast, where we discuss engineering concepts and applications found in everyday life. Hello, my name is Eric Vasquez. I am an associate professor in the Department of Chemical and Materials Engineering at the University of Dayton. I do this podcast as part of my teaching and research efforts. Today, we will be discussing about biodegradable polymers. We have our guest today is Ashley.
Hi, everybody.
And basically, we will be discussing quite a lot of the importance of biodegradable polymers and their potential to replace common plastics that are used in our daily lives. Before we get into biodegradable polymers, I think it's important to define what is a polymer itself.
Yeah, so a polymer is a macromolecule made up of repeating units, also called monomers. And so these monomers bond together during a process called polymerization, and that creates a long chain of these bonded monomers, and that's what we call a polymer. And so polymers are very desirable materials because they have a low density, which makes you can make lightweight materials out of them. They're very corrosion resistant and also relatively inexpensive. And you can fabricate them into different complex shapes pretty easily because they have low softening temperatures. And they're also great electrical insulators. One challenge, though, is they can melt at moderate temperatures, so they can be kind of temperature sensitive, and they also decompose at high temperatures. But overall, polymers are pretty versatile materials, and they're used in a lot of different applications.
Very good. So how are common polymers used in everyday life?
Yeah, so you kind of want to categorize the two different types of polymers. You have natural, which are derived from plants and animals, and then you have synthetic that are manufactured or derived from petrochemicals. And so natural polymers include things like proteins, DNA, cellulose, enzymes, wool and silk, and starches. Those are kind of the main categories of natural polymers. And then synthetic polymers include things like silicone, synthetic rubber, gels and adhesives. And then a lot of the clothes that you wear are made out of polymer fibers, such as nylon and polyester. And then kind of the main category that people think of when they think polymers is synthetic plastics. And so that includes polypropylene, which is used to make food packaging, and also polystyrene, also known as styrofoam. You can make styrofoam cups and containers. And then PTFE, also known as Teflon, is used as a nonstick coating on a lot of cookware, like pots and pans. Then you have PVC, or polyvinyl chloride. That's used to make PVC pipes, which is used in different plumbing applications. And then the last kind of major synthetic polymer is polyethylene terephthalate, or PET, and that's used to make plastic bottles.
Certainly, there are definitely a lot of uses in daily life, right?
Yeah, definitely.
But let's go back a little bit and let's talk more about these biodegradable polymers. What classifies them as biodegradable? Are there any standards that are used for this qualification?
Yeah, so in general, a polymer is considered biodegradable if existing microorganisms in the environment can break down the material. And when that material decomposes, it's normally breaks down into natural components like carbon dioxide, water, nitrogen, and components like that. And then those broken down components can be used by other plants and animals after that material has degraded. And so there's a couple different organizations that kind of classify polymers a little more specifically. One of them is the Federal Trade Commission, and so they classify polymers based on if the material can mineralize in 1 year or less. They consider that biodegradable. And then another organization is the Organization for Economic Cooperation and Development. So the U.S. is a part of that organization. And they kind of break it down into further based on different levels of biodegradability. So a highly biodegradable material breaks down within 10 days, and then they consider readily biodegradable if it breaks down majority within 28 days. And then intermediate biodegradability, it means that a material partially breaks down within that 28-day window, And then finally, if it's inherently biodegradable, it degrades a little bit, but it takes longer than that normal 28-day window. And then finally, there's also ASTM standards that can categorize biodegradability. And so they have different test methods and specifications depending on whether the biodegradable plastic is in controlled compost, in the soil, or in marine environments. The most common one is D6400. That's for biodegradable polymers in controlled compost.
Very good, very good. So when we talk about more on the chemical and the morphological structure, what kind of properties affect the polymer's ability to biodegrade?
Yeah, so there's kind of four main properties that determine a polymer's biodegradability. That includes crystallinity, cross-linking, molecular weight, and melting point. And so crystallinity is the degree of ordered atomic arrangement within the molecular chains of the material. And so no polymer is going to be completely crystalline. It'll have some highly structured crystalline areas, and then it'll also have random or disordered structures, and that is called amorphous. So most polymers are like a mix of crystalline and amorphous areas. And those higher crystallinity areas, that increases the strength of the polymer, and that leads to slower biodegradation because it's harder for those microorganisms or those enzymes to break down those tightly packed chains if you have a higher crystalline polymer. Cross-linking is also really important for biodegradability because cross-linking is the formation of bonds, which are usually covalent, and those bonds form between the polymer chains, and that creates kind of this like network of interconnected polymer chains. And so just like crystallinity, cross-linking also increases the strength of the polymer, which again reduces the biodegradability of that polymer. And that's because it's harder for that microorganism to break apart larger networks of polymer chains if they're more like tightly interwoven together from that cross-linking. And then cross-linking also reduces the ability of that polymer to dissolve or melt, and so that can also affect how it degrades in the environment. Molecular weight is another one that affects biodegradability. So as you link more monomers together, you're going to get a longer polymer chain, and that increases the molecular weight of your polymer. And as you get those longer polymer chains, those chains start to entangle with each other as they get longer and longer, and that also increases the strength of the polymer, and that makes depolymerization or the breaking down of that polymer a lot more difficult in the environment. And then finally, we have melting point, which is the temperature at which the crystalline regions within the polymer melt. And so as you have a higher melting point for a polymer, that increases the thermal stability of the polymer. And so that polymer is more likely to resist different environmental factors that would help break it down. So as you increase the melting point, you also increase generally the strength of the polymer, and then that reduces the biodegradability. So in general, a stronger polymer is usually less biodegradable.
I see. Yeah, that's interesting to know. So going into more of the chemical structure and the biodegradability, there was a study in 2020 that talked about biodegradable polymeric materials. So what are a few examples of this type of polymers and their current applications, if there are any?
Yeah, so I kind of mainly want to talk about the synthetic polymers because those kind of have a more application to replacing conventional, but one natural polymer is PHBV, and that's currently used in drug production and is slowly being used for food production or food packaging. But that polymer decomposes into CO2 and water. The problem is that it's pretty brittle in nature, so it's kind of hard to use it in certain applications. But for synthetic biodegradable polymers, one of them that's widely used is PVA, or polyvinyl alcohol. So that's used in glue, in different medications, and for food packaging. Another major application is laundry and dishwasher pods because it's a water-soluble polymer, and it's also readily biodegradable. Another water-soluble polymer is polyethylene glycol, or PEG. That one's commonly used as a binder or an emulsifier, and it's also readily biodegradable as well. Another large one that's used in a lot of different applications is polylactic acid, or PLA. That's being used a lot more in food packaging, but the main kind of application it's used for is medical and in the dental industry, and they use it for sutures and bone pins and different rods. And kind of a newer application that I saw for polylactic acid, it's used as a filament for 3D printing as kind of a more sustainable option. But polylactic acid is synthesized from more biomaterials like potato starch, wheat, corn, and more natural materials. So it's biocompatible and compostable. So that's kind of a really promising material. Another polymer that's derived from biomonomers is polyglycolic acid, or PGA. That's used in different tissue engineering applications and medical devices, and also in drug delivery. And then another polymer that's used in tissue engineering is polycaprolactone, but this one is synthesized from synthetic monomers, but it's also used in long-term drug and vaccine delivery applications too. And then finally, another major one is PBS, which is used in packaging and disposable items, and also in agricultural films and in biomedical devices. And PBS is also synthesized from synthetic monomers. But there's a lot of different natural polymers that are biodegradable, but they don't have as good of mechanical properties as those that can be synthesized and kind of more fine-tuned for certain applications.
Excellent. So there is a lot of concerns about pollution, right, with traditional plastics. Mm-hmm. So why are biodegradable polymers important in regard to the plastic industry? Can you give us some statistics, perhaps?
Yeah. So currently, over 4 million metric tons of plastic waste is produced per year, and that number is expected to grow to around 1 billion by the year 2050. So that's kind of a concerning statistics for plastics industry. And the other problem is only 9% of that plastic waste globally is recycled. And so almost 50% of it goes to landfills, around 22% is mismanaged, and then 19% is incinerated. And so you can get rid of plastic waste by incinerating it, but that significantly contributes to CO2 emissions when you burn it. So that's not exactly a great solution. So a lot of that plastic waste, if you kind of break it down by the different polymers, a lot of it is from polypropylene, which is around 62 million. And then if you look at the different polymer fibers, that's around 52 million. So that's like nylon and polyester. And then another big category that makes up the plastic waste is low density and high density polyethylene. And if you combine those, that's around 94 million. So those are kind of the top three categories. But then you also have PET, which is around 25 million. PVC is 21 million, and then polystyrene around 15 million, and polyurethane around 11 million. So all of those are kind of the main categories that contribute to plastic waste. And to really put things into perspective, those decomposition rates are like astronomical. So you really can't consider these polymers biodegradable. For example, nylon is used to make fishing line, and that takes around 600 years to degrade in marine environments. And then plastic bottles, which are made out of PET, and normally the caps of plastic bottles are made out of polypropylene, that takes around 450 years. And then plastic bags, which are made out of low density and high density polyethylene, that's around 20 years. So I think it's really important to try and find biodegradable replacements to try and slow the accumulation of all of this plastic waste that we are generating every year.
Certainly, that is definitely necessary for the world and the future generations. With the 3D printing of PLA, you put an example, right? Can you give us more details about which biodegradable polymers are most promising to replace common plastics?
Yeah, so it's kind of projected that around 41% of plastics are used for packaging, and half of that number is used for food wrapping specifically. So that's kind of the main area that I think would be more the best place to kind of target replacing conventional plastics with biodegradable polymers. And so kind of the most promising biodegradable polymer right now is that polylactic acid that I mentioned before. And a trademark name of that is EcoPLA, and that's currently made by Cargill Dow, which got renamed to a company called NatureWorks, and they're a U.S. company. But they currently make different sanitary products, sports clothes, and packaging out of that EcoPLA. And what makes polylactic acid really great is that it has a high strength, and when it breaks down, its decomposition products are non-toxic, so that's really good for food applications. And then it also has very similar properties to polystyrene, and it can be modified to have mimic the properties of polypropylene and polyethylene as well. So those three plastics are kind of one of the top categories that contribute to plastic waste. So that's why I think polylactic acid seems like the most promising choice. But there's a few other biodegradable polymers that could also help contribute to replacing common plastics. And one of those other ones is PBAT. It also has very excellent mechanical properties, and it has a very high strength. And just like PLA, it also has non-toxic decomposition products. It has a very similar flexibility to low-density polyethylene as well. So that could mean it's a good replacement for food packaging, shopping bags, and garbage bags as well. And then a couple other ones I kind of mentioned before, PHBV. So the trademark name of that is Biopol, and that's made by a company called Goodfellow in Great Britain. And they are currently using that to make razors and bottles. And so plastic bottles, we know, contribute a lot to plastic waste. So that could potentially be a good replacement. And then finally, looking at kind of a more natural alternative, we have starch. And so the American Excelsior company, based in the U.S., makes EcoFoam, and that is a starch-based loose fill packaging foam that could potentially replace styrofoam. And it can also be blended with PLA to use for food packaging and thin film packaging as well. And so out of those four, I think polylactic acid definitely seems like the top contender to replace conventional plastics, but the other ones have a good contribution as well.
Yeah, it's amazing. We can go from razors to bottles and all the different plastics that are used in daily life situations, right? So what is hindering the process? What are the main challenges with replacing conventional plastics with biodegradable polymers?
I would say the main challenge right now is the higher cost. So a lot of biodegradable polymers are made from bio-based raw materials, and that costs more to grow. And then it also requires a lot more specialized equipment to process those biodegradable polymers. So that's kind of the higher cost is, a big one because companies don't want to spend more money if, even if it's for the environment. But another challenge is I kind of talked about it before, the lower mechanical properties compared to fossil-based plastics. And so it's kind of a trade-off between strength and biodegradability. So if you want to make a polymer more biodegradable, you kind of have to decrease the strength a little bit. So that's one problem. And then another big one is the availability of agricultural land for those bio-based degradable polymers. And so you're going to be competing with land that's used for food production if you want to go grow crops that are used to create those bio-based polymers. And so that's a big one. It's just kind of competing for different land. And then the last one is the potential to complicate recycling processes for conventional polymers. So right now, the waste separation systems that's used to recycle conventional plastics, they can't really differentiate between biodegradable polymers and conventional polymers. And so when you have those biodegradable polymers mixed in within the recycling process, that can lead to treatment and quality issues because they have different properties. And so, although biodegradable polymers have a few challenges in relation to economics and infrastructure and processing mainly, I think they are definitely an important step towards becoming a more sustainable society, especially since the problem of plastic waste will only continue to get worse and grow.
Thank you, Ashley. Definitely, we have a lot of opportunities to grow and make better sustainable solutions for the future generations. Thank you for all the in-depth information you provided today. Has been very helpful.
Yeah, thank you for having me. I was glad I was able to provide some information on all the different biodegradable polymers and how we can potentially use them in the future and now. So,
Excellent.
Thank you.
Yeah, it will be interesting to see what happens in the next few years with these new types of polymers.
Yeah, for sure.
Thanks. Thank you all.